In this video we're going to learn a little bit about the motion of pendulums, and we're also going to simulate in SolidWorks an assembly of 15 pendulums, all of which will have different periods, and so when we release these and look at their motion only due to gravity, we'll see that they make some interesting patterns. But we'll begin by looking at the motion of a single pendulum, which of course is just the familiar back and forth motion here. And let's see what we can learn by looking at a free body diagram of the pendulum. So if we look at a free body diagram, then we'll call point A the point at which it rotates about, so the fixed point of rotation. The weight of the pendulum is through the center of mass, which is located at a distance d away from point A. And so if we take the sum of the moments about point A and set them equal to the mass moment of inertia about point A times the angular acceleration, well, the only force that creates a moment would be the weight at a horizontal distance of d times the sine of theta. And again, we'd set that equal to the mass moment of inertia times alpha, and of course alpha is the second derivative of the angle theta with respect to time. And so simplifying or rearranging that, we come up with the governing differential equation of the pendulum motion, which seems like a simple problem, but yet the governing equation is not so simple to find an exact solution for. It involves elliptic integrals, and so you usually have to expand that out into a series. But a lot of times we'll make the assumption that the angle is going to be small, so we never drop it from a great angle. And if that's the case, then the sine of the angle is approximately equal to the value of the angle in radians. And so if we substitute in theta for sine theta into the governing equation, we do have a simple solution to that. It's a simple cosine function. Theta naught here being the initial angle, so the angle that we release it from, and then let gravity take over. And if we go one step further then and calculate the period for the pendulum to make one complete cycle, then that turns out to be 2 pi times the square root of the mass moment of inertia divided by the weight times the distance. Now, before we go any further, let's take a look at what that small angle approximation means here. And I'm going to look at two pendulums, one of them being dropped from an angle of 5 degrees and the other one being dropped from 10 degrees. And I'm playing this in slow motion at a quarter speed so we can kind of see more clearly what's going on. And if you look, when one of the pendulums is vertical, the other one, as near as we can tell, is vertical also. So that would imply that the two of those have the same period, even though we drop them from different angles. I won't run the whole thing out, but I can show you the plot of angular velocity versus time for both of those. Now, of course, those are plotted on two different axes here, because the angular velocity of the one dropped from 10 degrees is going to, the maximum value is going to be greater than it is from 5 degrees. But the shape of the curves is almost identical. You can see that from this point to that point, something around 1.2 seconds. That would be the period of the pendulum, of each pendulum. And because of the fact that it seems like the curves are identical even after 8 or 10 cycles, it seems like the small angle approximation is certainly valid for 5 and 10 degrees. If I make this one, instead of dropping from 10 degrees, drop from 30, again, at the beginning it seems like we have exactly the same thing, that the period does seem to be, if not identical, at least close. And you can see we get a little bit of error as we run out further. They're not crossing when they're exactly vertical anymore. And so, showing a similar plot, you can see that as the cycles progress, then the curves diverge more and more. But still, if I'm looking at what the period is for each of those pendulums, it's still about 1.2 seconds. So a very small error introduced even at 30 degrees, but of course that error builds up the more cycles that we have. Okay, now we're going to look at a single pendulum here and calculate the mass moment of inertia of that, and we've actually used SolidWorks to do that. By the way, before we do that, there is a further simplification that you see in a lot of textbooks, and that is if the pendulum is just a ball on a wire, for example, and we assume that the wire is massless, then we can assume that the mass is concentrated out at a distance L away from point A, and in that case the mass moment of inertia about point A is simply going to be ml squared, just applying the parallel axis theorem to a point mass. The distance to the center mass, of course, is the same as this length L, and so you get the period by the more familiar equation 2 pi divided by the square root of L over G. But as we said, in our case, we're going to look at a pendulum that does not have a massless rod, and so we can use SolidWorks to get some of our properties. Let's go back and look at that again. If I go to mass properties here, by the way, you notice that I've defined a coordinate system because I want to know what the mass moment of inertia is about this local x-axis here. So here is my mass, which is actually, of course, the weight, since we're working in US units. And because I've chosen, instead of the default origin of the assembly, if I pick coordinate system 1, then I can come down in here and it says mass moments of inertia taken at the output coordinate system. The one about the local x-axis is the one I want, 30.89. So let's go ahead and close that. Go back to our example here. And so there's the 30.894 that we pulled off. And remember, that was in US units pound inches squared. So I need to divide that by G so to have a consistent set of units. And since I'm working in inches, 386.1 inches per second squared. The distance to the center of mass also got off of SolidWorks, and so the period that I calculate is 1.16 seconds. Let's see how well that agrees. And again, I'm running this from a drop angle of 30 degrees. And so I expect to have a little bit of error in there, but you can see that the period that shows up here is about 1.16, 1.17 seconds. And so I can get the exact value by exporting the data off of this curve, and as long as I've used a lot of data points, I can get very close as to what the exact value of the period is. Before I leave this and go back to the 15 pendulums in just a moment, this is the effect if I drop this from 90 degrees. If I go and look at the, again, a plot of angular velocity versus time, you can see my period now is all the way out here to about 1.35 seconds. So now we've got a significant amount of error if I use the small angle approximation. The other thing you notice here is, as we said earlier, with the small angle approximation we had a perfect cosine wave. And in this case you can see that we're kind of flattened out a little bit. And again, we use the exact solution uses elliptic functions instead of circular trig functions. And so you see that effect as you get further away from the small angle approximation. But let's go now and look at the 15 pendulum assembly. So the one we just looked at, that would be the first one right here. And the period that we calculated means that this will pendulum over a period of 1 minute will make exactly 51 cycles. The one next to it has been designed so that that one will make 52 cycles, the next one 53, and so on. So after a period of 1 minute, all the pendulums will come back to their original starting position, and in between, as we said, they make some kind of interesting patterns. So let's let it go. Again, they've all been released from 30 degrees, and so we'll shift around so we're looking from the side view. And at times it'll seem like the pattern seems to be kind of random, and then you get some waves going here. And in just a little bit, when we get to the 30-second point, this whole thing lasts for 2 minutes. When we get to the 30-second point, about right there, half the pendulums are on one side and half of them are on the other. And that's because the ones that make an even number of complete cycles over 1 minute will have completed an integer number of cycles in a half a minute. The ones that are odd numbers will have completed an integer number plus a half of a cycle after 30 seconds. So again, we ended up with half of them on one side and half of them the other. We're almost to the end of 1 minute right there, and so they're all back at 30 degrees. And in this case, we're just going to shift around and look at the top view, just a different perspective on it, and just let it go for the rest of the 1 minute total cycle. Right there is about the 30-second time period when half of them will be on one side and half on the other. And we're approaching the end where they'll all end up back where they started from.